Okay, so in this chapter we're going to talk about chemistry. But before you panic, it's not going to be that much. It'll actually be just the basics of chemistry that you're going to need to know to survive A&P 1 and A&P 2. So, yay! Okay, so just some basic principles. A couple definitions here for you. Chemistry is a science of structure and interactions in matter. And matter is anything that occupies space and has mass. So mass is defined as the amount of matter a substance contains, and weight is the force of gravity acting on mass. Now in science, one of the things, and even in anatomy, what you're going to find is that the common way that we talk about things in the everyday world are going to be very different than what the terms we use in science. So technically, while we say, how much do you weigh when you step on a scale, in science, what you're actually getting is something's mass. It's not its weight. In order to get something's weight, you'd have to multiply that by the force of gravity. So just something to keep in mind and something to sort of get used to, because again, as we progress along the semester, we'll see some other examples of that. We'll be talking about lots of different chemical elements and how they affect the body. We'll be using them in different equations and formulas and how they work together. We'll be talking about different ions and stuff like that. So it's important to remember that matter is going to be composed of chemical elements, and so these are things that cannot be split into simpler substances. Okay. We'll be talking quite a bit about oxygen, carbon, hydrogen, some about nitrogen. We'll talk more about that once you actually get into 202. We'll also be talking a lot about calcium, about sodium, and potassium as well. They'll be very important in the way muscles fire as well as how neurons fire. So that'll be toward the end of 201. Again, just kind of a reminder to you, atoms are made up of a nucleus and then this cloud of electrons around it. The nucleus has protons, which are positively charged, and neutrons that are neutrally charged, and then electrons will balance out the protons. Okay, and if you kind of remember, you may have heard of this in a chemistry class or in high school. An ion is basically an atom that has either given up or gained an electron. So if it has given up an electron, it's positively charged because it's lost a negative charge, right? So it would have a negative sign. If it has gained, or I'm sorry, it would have a positive charge. If it has gained an electron, it would have one extra, so it'd be negatively charged, so it'd have a little negative. So again, if it gives up an electron, it's positively charged. If it gains one, it would be negatively charged. So then a molecule is simply atoms that are going to share electrons. So a classic molecule that you will see over and over again is dihydrogen monoxide, H2O, more commonly referred to as water, right? It's probably how you know it. It's H2O. All right. So then the real question is, why do atoms give up or gain or share electrons? What's the whole point of that? If you remember back to, again, some high school chemistry, hopefully you'll remember the concept of a valence shell. So it has the outermost shell of electrons, right? And atoms are going to want, if these things can want anything, they don't have a consciousness, but they're going to want 8 electrons in that outermost shell. The exception being hydrogen that only wants 2. Okay, so to complete that 8, they're either going to give up some to get that 8, gain some to make up that 8, or they'll simply share. So they can both have 8. Okay. What happens is ever so often you have an atom or a group of atoms or a molecule that has an unpaired electron in its outermost shell. These are highly reactive. Oftentimes what they end up doing, you can see in this second bullet point here, is that they'll actually take an electron from another molecule. Okay? And what ends up happening is that by taking that electron from another molecule, it breaks them apart. So you start damaging tissue in the body. Okay, so you have other substances, I mean, you've probably heard about this in the news all the time, how great it is to have antioxidants. Basically, oxygen, in this, you kind of see this image down here, A superoxide free radical is a classic example floating around in your body. Now you see it has this unpaired electron, so it will try to steal one from another molecule, break things apart. Antioxidants are going to inactivate these oxygen-derived free radicals. Okay, so they'll help prevent any kind of damage to tissue. All right, so we're just going to talk a little bit about chemical bonds. Okay, particularly these are going to be important as we start talking about water, pH, and some chemical reactions. Right. So again, as I mentioned to you earlier, one of the major driving forces in chemical bonds or ionic bonds or forming of ions is the number of electrons in this valence shell. When we talk about positively charged ions, we call them cations. When they are negatively charged, we call those anions. So again, just some terms that you should be familiar with. Later on, I will be using these terms cations and anions more frequently than simply saying positively or negatively charged ions. Now, covalent bonds are formed by atoms that share electrons, and they form these things called covalent bonds. So here's a nice example of two hydrogen atoms. This one has one, this one has one. Again, remember they want to have two. They're the one exception. So they're like, hey, I'll share that with you, and then they both have two, and they're both happy. Same thing with oxygen atoms. They'll actually form a double bond. So this one will share two, this one will share two, and then they both have a full complement. Nitrogen will do the same, but with six. Total 3 each. And then carbon is one of our classic ones. So it has 4 electrons in its valence shell. Hydrogen, each hydrogen has 1. So there will be 4 hydrogens to 1 carbon because each one will share. So it's 2, 2, 2, 2, or 8 for carbon, right? So everyone's very happy. It's a very stable molecule. So when they're nice and evenly shared, we say that that's a non-polar covalent bond. Right? When these electrons are not shared equally, we call those polar covalent bonds. Okay? And in this case, this idea of polar, you'll see this term again come up several times in anatomy in different places. That term polar simply means it has different ends, or the ends of it are different. So you can think of it like North Pole and South Pole of the Earth, right? They're 2 different ends, if you will, of our planet. So one of the most classic and maybe even important polar covalent bonds is that of water. So again, here we have oxygen. It's missing 2 electrons in its outer shell. Again, we have 2 hydrogens, so they can both share, right? But here's the deal, and you can kind of see this. Oxygen is a much larger atom than either one of the hydrogens. So it holds on to those electrons a little bit more tightly and for a little bit longer than it allows hydrogen to have them. So what ends up happening is that instead of sharing it equally, it shares it unequally, and so now you have 2 different ends. So the end that has the electron more times ends up having a slightly negative charge. So then the part that has the 2 hydrogens ends up having a slightly positive charge. Okay, so you can kind of see this. You have this Greek delta sign. So it's delta positive by the hydrogen, delta negative by the oxygen. Why this is so important is that this allows for the formation of hydrogen bonds. So here in this image, what you're seeing is this slightly negative part of this water molecule at the oxygen will be attracted to the slightly positive hydrogen and vice versa. Again, same thing with this molecule. Slightly negative oxygen part will be attracted to the slightly positive hydrogen part, and so on, so forth. So this forms these hydrogen bonds. Now, a single hydrogen bond is not necessarily that strong. However, many of them put together are. I'll give you a great example of a hydrogen bond. If you were to wet your hair and then braid it, right, and let it dry, your straight hair, presuming you start with straight hair, would then become wavy when you took the braid out. Magic? No. What ended up happening is as your hair was wet and as it dried, and so you braided it, and as it dried, those hydrogen bonds reformed themselves, so gave your hair this temporary wavy-like appearance. It's not a permanent thing. It's not a permanent chemical change to the makeup of the hair itself that you would see in something like a perm or something like that. But these temporary little hydrogen bonds are strong enough to cause waves in hair. The other wonderful thing that these hydrogen bonds then do is they cause water to have a high heat capacity. So what this means, if you take a look at this image, and let me get my pen ready here, is if we apply the same amount of heat to both water as well as to land, you'll see that it will simply raise the temperature of water 1 degree, right? Whereas it will actually raise the temperature on the land 5 degrees. Why? Because the energy that's being put into this water, what ends up happening is it's first used to break apart all those hydrogen bonds. So as it's breaking apart the hydrogen bonds, the temperature stays constant. And finally, once all those hydrogen bonds are broken, that's when the temperature starts to rise. Okay? It's also one of the reasons why, when you think about this, you already know this intuitively. If you were to boil water, like you take a pot, like a metal pot, stick it on your stove, you've got some water in there, and you turn the heat on, right? After a minute or two, you'd probably be fairly confident that you could put your hand in the water and it would still be, fairly tepid. However, if you were to touch the metal sides of the pot, it would be really hot and you'd probably end up burning yourself, right? Again, that is caused by what's ending up happening is that you have all those hydrogen bonds in that water that are being broken, so the temperature hasn't risen yet. It's going to take much longer, and eventually they will, and eventually your water will actually boil. So it's kind of like a real nifty real-life application. What this also means is that the heat of vaporization is also high, so that you have to put in more heat to change it from a liquid to a gas. That's what makes sweating so efficient. That's what makes those misters work so well in the summertime here in Arizona. You can also see that those hydrogen bonds are going to keep those water molecules actually together. Now, us big things, it doesn't help us. We're too heavy. Again, these bonds aren't that strong. But for small animals like this water strider, they can actually be right on top of those water, without ever breaking those hydrogen bonds. So it's kind of like they're almost like on saran wrap. The other place where you can see this high surface tension, and you probably had this happen, if you're ever filling up like a glass with water and you kind of overfill it a little bit, so you can actually see where there's a little bit of water just above the top part of the glass. Okay, so that again is high surface tension. You can do that to a certain point and those hydrogen bonds will keep that water together. Too much, or if you shake it, it'll overcome those small bonds, and yes, it'll spill over the side. But just a little bit, it actually holds it together. Now, unfortunately, if you end up having fluid in the lungs, what ends up happening is that surface tension would actually keep the small little air sacs in your lungs closed, so they wouldn't allow them to inflate. So obviously you don't want to have fluid in your lungs. It can affect respiratory function. Okay. Water is super important. It's going to be part of mucus, lubricating fluids. So you'll find it in a lot of the fluids that you'll find in your joints, in parts of your digestive tract where you have to keep food moving along nice and smoothly. Basically, wherever friction needs to be reduced or eliminated, you will find water making up part of the fluids. Okay. Again, water, I cannot state this enough, it's going to be a very important inorganic compound in all living systems. You may have been hearing about even NASA looking for water on Mars. Well, this is because water has such an important role to play in all of life's functions. So some other things that it does is adding water molecules will break large water molecules down into simpler ones. So we call that hydrolysis. Okay, so hydro meaning water, and lysis to break apart. So water breaks apart bonds. Dehydration synthesis, on the other hand, if we take water out of something, molecules will actually join together. So we can form a larger molecule from two smaller ones by simply taking the water out. We call that dehydration synthesis. Water acts as a very good solvent. So a solvent is something that will dissolve a solute. Okay, so for example, water, the solvent, will dissolve salt, right? You know that, like you can put some salt in your water and it'll dissolve it. It can give you, but other things can be solvents. It's not just water. It just acts as a very universal one. It does dissolve a lot of things, not everything. Oils, for example, will not dissolve in water. However, vast majority of things do. Another example that I like to give is sort of like if you have milk and then, like, I don't know, hot chocolate or a chocolate powder, or Hershey's Quick or something like that. Basically, the water is the solvent and it'll dissolve like that chocolate powder, right? You get chocolate milk. If the substance dissolves in water, it is considered hydrophilic. So salt would be considered hydrophilic. If a substance does not dissolve in water, it is considered hydrophobic. So again, as I mentioned earlier, fats, oils, anything that's fat-based will not dissolve in water. The way that water actually acts as a solvent is really cool. I get super geeked out, excited about this because I think it's like one of the niftiest things in the world. Basically, like, so you probably have all had this experience, right? So you've got your water in a glass and you're adding something to dissolve in it. I don't know if you've done it with salt, but maybe some sort of, like, I don't know, lemonade powder or something, right? You're making something. So you put a little bit in, you stir it, and it works fine. So you're like, oh, you know what, I'll put some more in. You stir it, it's fine. You put maybe like a third spoon in, and all of a sudden, no matter how much you stir, you're going to have a little bit on the bottom that's just not dissolving no matter how much you want it to. Okay, this is why that happens. So the example given here is actually sodium chloride, so salt, right? So kind of classic table salt. So salt is made up of sodium that has a positive charge and chloride that has a negative charge, right? So remember, our water molecule has a slightly positive end or pole, and it has a slightly negative end or pole. So guess what? That slightly negative end aligns itself, kind of, I don't know, crowds around, totally encircles that slightly positive sodium, right? So they're attracted to one another. And exactly the opposite, that slightly positive end is going to be attracted to this negative chloride. Okay, so again, it kind of crowds around and circles it. Now imagine this is a 3D structure, so it's just kind of forms like this bubble around it. Well, at some point in your glass, you simply run out of water molecules to crowd around that salt that you put into it. So the reason why it precipitates to the bottom, it doesn't go into solution anymore, you've run out of water molecules to surround it, to hold it up. Isn't that kind of cool? That's what's actually happening. You're actually running out. You found that point when you've run out of water molecules. Is the time when it's settling on the bottom. I guess I just think that's pretty cool. All right, so hopefully everyone's doing fine. Take this opportunity, take the quick quiz. Just a few points. Again, make sure you're understanding things. If you're not, you can always feel free to email me.